Good afternoon. The topic of my presentation is an interdisciplinary project carried out together with Dr. Urszula Warzyńska and Dr. Tomasz Siwulski. It is a part of my ongoing project of PhD, which focuses on tubular bone artifacts from Eneolithic sites in Central Europe. My research examines whether the bone specimens may have played a role of sound generators. However, this presentation is limited to the aspect of the digital sound reconstruction using a group of bone tubes attributed to the Neolithic early Bronze Age Corded Ware culture. During an experiment, we used CFD simulation. CFD is a branch of fluid mechanics that uses numerical methods to solve fluid flow problems. It is also applied during studies of gas mechanics. In this case, the non-destructive nature of digital sound reconstruction also is significant. Each step of analysis based on digital models. The aim of the project was to determine the pitch and sound intensity of models of archaeological edge fluids as a function of airflow velocity. The project involved several stages, including physical testing and modeling of 3D digital versions of the artifacts. The measurements were conducted at the Laboratory of Working Machines and Fluid System Diagnostics at Wrocław University of Science and Technology. The following slide shows the detailed maps of sites which provide discussed finds. Next, the images present the artifacts of the Corded Ware culture involved in the digital sound reconstruction. Those artifacts were recorded in graves, mostly as single finds. The exceptions are objects from the Moravian Kostelec na Hané and the Lesser Poland Giebułtów. The studied artifacts vary in many aspects, including state of preservation. The best state of preservation is presented by KW1 and KW2 from Książnice Wielkie. Both specimens are made of bird bones. Other artifacts were made of mammal bones, sheep or goat. Some of them, like finds from Giebułtów, G6 and G8, and K2 from Koniusza, bear the traces of decoration. All the artifacts contain specifically elaborated ends from one or two sides. This brings the objects closer to being interpreted as edge flutes. In such instruments, the beveled end creates the sound. As I have mentioned before, the project involved physical tests. At this point, I would like to show you the pipes included in the physical test. Specimens called B1 and B2 come from an experiment presented at the EAC 2 years ago. Later, I prepared another one, B3, using the same method. I recorded the course of experiment. During processing, I used specific flint, which was recognized at the archaeological site, and bone sandstone as polisher coolite. B1 and B2 are made from the bones of sheep, while the raw material for B3 is a crane bone. The real results were the basis for verification of the CFD method for conducting numerical airflow simulations developed at a later stage. The test stand was conducted in a noise-free chamber. The test included following elements: a compressed air supply, a flow measurement, a throttle valve, a nozzle, an examined object, a sonometer, a microphone, and a measurement computer. This stand allowed for the reduction of variables. The picture on the right illustrates the position of the B2 specimen during the measurements. The yellow cover plays the same role as the instrumentalist's lower lip. It is worth noting that the successful positioning of the nozzle relative to the pipe was not easy. Minimal misalignments causes the sound to disappear. This is also observed when the instrumentalist is producing the sound. On the left, the sound spectrum is visible. The table shows measurements of the loudness and frequency of the sound obtained. As you can see, amplification also occurs outside the range of human hearing. This ends around 20,000 Hz. In the next step, the CFD flow simulation has been prepared using bone replicas of the artifacts created during experiment. This process is visualized in the following diagram. The starting point is the analysis and preparation of experimental results presented on the previous slide. Preparation of 3D models for numerical simulation based on CT scans. Here we can see a figure that combines a CT scan with photogrammetric imaging to show the position of the pipe in relation to the earth source. For each test object, photogrammetry of position was taken. Next, the discretization of geometric models and the preparation of numerical models. And finally, implementation of CFD numerical calculation was done. Here you can see visualization of the air velocity field, and here you can observe the lines in the airflow. The last point leads us to the analysis of the results of numerical simulations and their verification with experimental results. The frequencies and loudness readings from the physical test and the CFD simulations are correlated to some extent. The lowest frequency peak is 2562 Hz for the physical test and 2169 Hz for the simulation. In the case of loudness, the value obtained during the simulation is with the range of loudness obtained during the physical test. The graph on the right shows the relationship between decibels and hertz for the physical test, it's orange line, and CFD simulation, this is blue line. The visible differences may be due to the presence of equipment and flat surfaces during the physical test, which may have influenced the amplification of the drift frequencies. The results of CFD calculations were greatly influenced by the accurate representation of the pipe, nozzle, and cover locations relative to each other. In addition, the deviation of the experimental SPL characteristic relative to the simulated one may result from the adopted parameters of the calculation models, for example, the mesh density and the discrete model and others. Before presenting the results of the CFD simulations of the bone artifact, it is necessary to describe how their digital 3D reconstructions were obtained. The process consisted of modeling the photogrammetry data. These are 3D models of artifacts with incomplete internal geometry, supplementing them with internal geometry and possible reconstructing cavities resulting from the state of preservation of the artifact. Photogrammetry was carried out in Agisoft software. The graphic on the left is a screenshot from this program. The blue rectangles correspond to the photographs of the artifacts that make up the photogrammetric model. Later modeling was performed in Blender. The internal geometry of the pipes affects the sound quality. Given the post-deposition processes, we cannot assume that the inner part of the artifact is the same as when they were produced. It was therefore decided to use microsomography of contemporary created sites, B1, B2, B3, to model the interior of digital 3D reconstructions. Digital 3D reconstructions of the artifacts were given internal geometric surface made from fresh tubes made from bird bones, B3, and from fresh tubes made from mammal bones, B1 and B2, respectively. I am presenting the simulation results using the example of the artifact from Szczepanowice. Amplifications at individual frequencies are visible, including those beyond the limits of human hearing. The frequency with the highest SPL is 1686 Hz, which corresponds to the musical sound G#6. The loudness is considerable at 69.34 decibels. Admittedly, it does not go beyond the pain limit, but it is worth noting that such a loudness level at such a frequency can already be perceived negatively. All of the artifacts tested were capable of generating sounds audible to humans. In the spectrum of the reconstructed sound, high frequencies are prominent. The sound is perceived as loud and high, which makes such a sound unlikely to be considered pleasant for the listener. On the other hand, it is specific and different from the sounds of surrounding world. The artifacts come from graves of the Corded Ware culture. The economy of this society was based on cattle and sheep farming. The Corded Ware culture population is characterized by a relatively mobile lifestyle. Ethnographic data shows that this type of community used sound tools with signaling or deterrent functions. The presence of frequencies that are not perceptible to the human ear may indicate that the tubes were used in accordance to animals that can hear higher sounds. This could suggest that the tubes were used, for example, to make animals aware or call them. Bone tubes could serve as signaling devices, deterrents, or decoys. The next slide shows the interpretation of the results. Thank you very much for your attention.